try everything.
Thank you for indulging us. It's adorable to see two very young kids spinning around, wiggling their bums to this song. We've been doing that this weekend. And the only non-Canadian song on the playlist for 1070. So I think we did pretty well representing
we did
Canadian
really
music.
well about that, but it's maybe the one that's most about the stress that people might feel at this time of year.
It's like the COVID anthem.
Try everything.
Try everything. Okay.
Birds don't just fly, they fall down and
So,
get up.
Smith, today,
Dr. Jacobs.
we have like to get
Non
through
sequitur, non sequitur, non sequitur.
No detours.
Oh yeah,
No getting off track. You keep us on track, and we will finish by the end of today. This is our goal.
What do you mean by finish?
We will finish the course by the end of today. This is the goal, which means we're not going away. We're not going to stop being available during normal class
Oh yeah,
times.
this Zoom class is always here.
We're just always
We just
gonna
turned
be
it
here.
on.
Monday and Wednesday. You can join us next semester.
Hello.
So if we get through today, we will not be canceling anything, but it's entirely then your time, and you decide if you want to join us to ask questions as you prepare for the exams and things like this. We're also going to do that even though there is no class on Monday. Next Monday, we're going to be available during class time if you have any questions in anticipation of the exam. So all of that stuff, though, we're going to repeat and post in an announcement once we know that we're actually able to get through everything for today. So are you ready?
Should we post the lyrics to that song?
Are you ready? Let's get going. But
Yeah, let's get
first, screen grab,
I did it.
all of that, please.
Oh, I did it.
Yay! It's so pretty. It's our pot-smoking fish. Yay.
420
Does that
fish.
make it a fish head?
Oh, it's a pa-fish.
It's a fish. Okay. Yeah, I hope there are people out there that know that, because I was like a monster fish head when I was a kid.
Yeah.
Yeah. Like, yeah.
The aura is still there.
The braids, the dreads, the whole deal. Okay.
Yes,
Yes.
both dreaded. Both of us. At one point.
Oh my god.
Yeah.
Embarrassing. Okay.
No,
So-
mine were splendid.
Yours were splendid?
Oh, yeah.
Okay, here we go. Ready? Let's
3, 2,
clear.
1.
Clear. Thank you. Are you not going to clear?
Do you want me to clear?
Yeah, clear. Okay.
Sure.
That's okay. I can get there. It's just
I got
really
there.
awkward. Okay, here we go. A body with different temperatures across the body, and this is an important concept that we're going to be sort of reviewing. I believe that you've seen quite a few of these things. These are just kind of bits and pieces that we're wrapping up from the stuff that you've already done in the asynchronous part of this course, but we just thought that we would kind of hone in on some of the key vocabulary, the key concepts. That's important to keep in mind.
This is really quiet.
Oh, it's really quiet. Okay. I think everything's fine. How about, wait, we can just move it. How about this? Is that better? Okay. We'll try that. Some of you are having some trouble coming in because I've seen your names pop up several times in the waiting room. I hope that you can join us. Okay, here we go.
If you're still having trouble here, just tell us.
Let
in
us
the
know.
chat.
It's
Oh,
better
better
now. Yay. Good. Okay. Cool. Here are some things that we hope that you will be able to do by the end of this class and also by the end of this course. We'll walk you through them and show you how these things connect. But first, some homework. We gave you some homework to do the mammoth and the icefish story all the way down to the very bottom. And if you were able to do this homework, then you should be able to answer a poll question that I'm going to throw at you right now. So here's the poll question.
It's pretty violent.
It is pretty violent. Throw at you.
Throw near.
That I'm going to share
Offer.
with you.
I'm going to offer it to you.
I'm going to offer it to you.
You may take it if you wish.
Here you go. Here's a poll question.
Bam!
Bam! And then you can also read it on the slide. Here you go. What's the answer?
Probably it depends, isn't it?
I'm going to mute you.
I think it's often it depends.
Okay, what a statement is true. In an endotherm, the environmental context is not important.
Sorry, I can't read anything. Because of this goddamn program. Like, it doesn't accept being in the background.
Yeah. Okay, here.
Yeah.
Hi.
It's pretty low attendance.
Is it? Yeah.
There's close to 500 some.
Yeah.
What's the stats on the studio look like? Pretty low. Hope that somebody liked. You fuck off, YouTube.
Okay, I'm now unmuting.
Oh yeah? Less swearing?
Okay, we'll just give you another 30 seconds. You're doing great.
Can I remind them about 19?
Yeah, sure.
Thanks to whoever that was.
Yeah. I don't think anyone else noticed.
But that might be a good reason to tell them.
Yeah, sure. Okay. And before we go to the answer, Smith has an announcement.
Those of you who've been joining asynchronously or following up asynchronously, we're in lecture 22, I think now. Back on the 19th, something happened in the interpipes, and the last 10 minutes of the lecture weren't on the lecture 19 YouTube, the original posting. So there is now a part 2 online.
So it's all fixed.
It's all fixed. Just make sure you don't miss those final 10 minutes, because there were lots of questions about it, if I remember that, because that was the final 10 minutes about mitochondrial inheritance versus nuclear inheritance versus, and there was
cool.
there were questions.
Yay, cool. Okay.
So, polling schmoling.
The
Well done, you.
biggest category, 51% of you got the correct answer, yes. For the rest of you, these are not super easy sentences to pull apart. So if you felt like you needed more time or you didn't get to do the homework and you were just trying to evaluate them right now, no worries at all. These are, again, not simple and quick answers to come by. But we do hope that you kind of get the feel for it in terms of, like, you know, preparing for the final. We do a lot of true false, right? All of these are essentially true false, and you have to, in this one, pick the true one. The rest of them are incorrect, and they're incorrect for different reasons. So that would be a good study opportunity to go back and to take a look at them. And of course, they'll be available in the slides. Okay, let's just go if you're okay with it. Very quickly, we want to just make sure that we get you to really appreciate the homeoviscous adaptation. This stuff was covered in course link, but we'll kind of just go over it really, really quickly now, because I think it's really cool. I love, like, how all of the things go from, like, these big ecological sort of, ways of being and different relationships and all of these things, right down to the molecular level where molecules are acting like they're in ecosystems, right? And it's just amazing to me how some of the physical properties of the molecules themselves, not just the chemical composition, but the physical properties of the molecules, have quite a deep-seated connection to function. And in fact, that's one of the things that to me is fascinating about nature, is that if you take a look at nature and the way that sort of biological systems solve problems, a lot of it has to do with form that serves function. And when we think about like technological solutions, the ones that we try to solve, we end up for the most part just throwing energy at that problem to make it faster, bigger, and better. Nature tends to modify structure in order to be able to create new function. One of the best examples of that, of course, is proteins, right? It's the form, the shape that determines the function. And here we have another instance of that. And why do I think that that's amazing? Because if you can change your shape without increasing energy, then you're not really contributing to like greenhouse gases and things like this quite in the way that we do, right?
So you just made a jump from to human systems.
Yes. I totally, did you see? I did that. But anyway, so when you think about, when you hear like scientists from the UN talk about needing to or wanting to explore natural systems, that's what they mean, learning from natural systems to understand how they solve problems. Generally can lead to more sustainable solutions. Mm-hmm. So homeoviscous adaptation is an example of that, where form leads to function. So basically what we're talking about specifically has to do with the fluidity of the cell membrane in the context of different temperatures. And what is going on here is basically taking all of the stuff that we learn about, you know, saturated and unsaturated fats and which ones are good for you, which ones are bad for you, and all of that stuff. But here's kind of why those things are the way that they are, okay? So saturated fats have no double bonds. Basically what a fat is like a string of carbon chains next to another string of carbon chains, and sometimes they can be two of them. And if we're talking about nutritional fat, we're talking about three of them being combined. Those are triglycerides. These are not. These are the fat molecules that exist to make up the cell membrane. So they're basically these two strings of carbon. And they can be either connected by double or single, sometimes triple, but we're not even going to go there, double or single bonds. And every time there's a double bond, it creates a physical kink in the little tail of the carbon chain. And that physical kink, if you take a look here at the difference between these three next to these three, that physical kink creates spaces physically, like it makes real changes. It occupies more space. And when it occupies more space, it means that it's more fluid, right? And this is really important to have more fluid cell membranes in the context of a cold environment, because in a cold environment or a low energy environment, things tend to get more solid, right? Jam-packed together. If you increase the number of double bonds in your carbon chains, in your lipid bilayer, you end up with something that's a little bit more fluid. It means more things can pass. There's more exchange, the way that, you know, a cell would want to have these controlled membranes rather than these sort of solid brick walls, right? And so that's really the difference. So basically, you know, species that have this homeoviscous adaptation use this particular function of these unsaturated fatty acids to compensate for the decrease in energy, the decrease in fluidity associated with a cold environment. Aha! And now something completely different. Did you have anything that you want to say about the homeoviscous adaptation before we go?
My enthusiasm for it is dwarfed by your own.
Oh. Okay. That's so diplomatic. So he said, if you ever want to say I don't give a shit about something, you can say my enthusiasm is dwarfed by yours. It's delightful. Well done. Okay. Now, when I was what?
Before you start that,
okay.
There were a couple of Easter eggs on those last two slides when you're studying.
Yes. Were there?
Yeah.
Okay.
So think about graphing those how those kinds of things are expressed, how we might find graphs, and then ask you the kind of question, well, what kind of things from this graph can you tell me likely about cell membranes?
Because you totally know we do that by now, right? Good.
Right?
Okay. Okay, so when I was not a professor, I was a polar expedition leader. I think you know this. And I spent a lot of time traveling in the Arctic and the Antarctic. And inevitably, I would be traveling in the Antarctic where there are penguins with people that were not necessarily biologists. Maybe they were camera crew, or maybe they were, super rich tourists. And this question would come up all the time. The question is, why don't penguins' feet freeze? It's a great question. And the answer is they kind of do. So
Silly humans.
Silly human. Somebody who is a biologist probably wouldn't ask that question, unless they were if they were like a cheetah biologist and they had no idea, then for sure. But an informed biologist about this particular topic wouldn't ask that question.
Questions.
It would be a different question. And the question would be, why don't penguins freeze? Different question, right? Focusing on a different area of the body. And so in order to get to that question and to answer it, we have to talk about something called regional heterothermy, okay? And I believe we've already touched on this, but let's just make sure that we all fully understand what regional heterothermy is. And you can break it down, regional, right? It's not national, it's regional. So that means areas within, okay?
But not geopolitical areas.
Shh.
You said national.
Right? Or sort of not organismal, but regional. So within the organism, there are regions. Hetero, usually meaning two. Thermy, right? Or multiple hetero.
Yeah.
Thermy, temperature. So areas of the body of different temperature. That's how you get to that, right? We're not very creative when it comes to scientific terms, although sometimes we are entirely wrong. So just keep that in mind too. There are complete misnomers, like the crab-eater seal.
Right.
It doesn't eat crab, but it is a seal. And there are some other things, like what is it? The potato ant that is neither an ant. No, the panda ant.
You are so...
Am I wrong?
You were like, you keep saying Smith, no non sequitur. Smith, and you're like, potato ant.
No.
Isn't it like the
No, it
potato
started
ant?
with a P. It was the panda ant.
There
It is
is-
neither a panda nor an ant. I'm just saying. Okay.
Oh my god.
Sorry.
I realize I'm gonna. Okay. Where are these reins? I've got them down here
Rein
somewhere.
them in. Okay. And regional heterothermy.
I love this.
You do. Why don't you talk about
No,
this?
I don't. I can talk about some other things later on, but
Yeah.
this is, to me, this is elegant and beautiful. And oh my god, I wished I had this at certain points. And I stuck in a couple of pictures later on about these kinds of things. So these are adaptations in regional heterothermy. That's where I wanted to go in your last non sequitur, was the fact that sometimes when you're presented with new words and you think, why the hell, what is this? Think of where it's derived from, and then its explanation is there. This is true for species names, and it's true for a lot of biological principles like this. So in what way can we have parts of the body that are at a different temperature than the rest of it? Well, this is a great example of it. It is in the flukes and flippers of whales and seals, lots of northern aquatic things, and in the legs of wading birds, northern birds, caribou, and wolves. And of course, northern wading birds are also southern wading birds. So this is an adaptation too cold that they carry around with them as they move positions on the globe. We call it counter current flow. So you've got arteries carrying like hot blood from the center, the protected core. This is an endotherm thing, right? We're strictly talking about endotherms right now. Out to the distal parts of the body, like the flippers. So hold up your flippers. And we've got cold venous blood that's been exposed to that nice kind of what's Happy Feet tap dancing. So he's tap dancing on the Antarctic, and though his flippers are then super cold, and so the venous system that's bringing blood back is cold. And if that arrives at his heart, Happy Feet is not a happy penguin. So what's happened is the wrapping of that venous system around the arterial system, so that the cold blood is rewarmed by the blood that's leaving the hot blood. That's amazing.
It's amazing. So
What a happy accident.
yeah, right near the toes, it's actually just above freezing,
Yeah.
right? Like it is not much different than freezing temperature.
The-
As you move up the legs, it becomes warmer and warmer. And what's people always think that penguins have really short legs, right? Because you can see that here there's not much exposed, but that's actually not true.
Yeah, you need to see an x-ray.
Yeah, if you take a look, like even
right
at
here.
that penguin here, I'll
Yeah,
show
go-
you.
go and do it.
Even the penguin over here.
Come on, Lily. Point with Lily.
No, come here. This is a chin strap penguin. Okay? And
You think leg.
you think leg from
Wah.
here down, right? But actually, no. But actually, here is their knee. Or their knee is here and their hip is here.
Yeah.
Hip is up here. And so what they've evolved is this layer of belly fat, gut. Like imagine basically the biggest beer belly possible.
It's the biggest man
that
gut.
gets that gets dragged down over their knees, right?
Like no belt buckle visible.
Kind of like a skirt, right? To keep their warm muscles, their big quads, nice and warm and protected. And then only the sort of bare bones and the tendons and sinewy parts are exposed with very few muscles in the feet. Only the ones that you need just enough. Just enough. So penguins actually have pretty long feet. And if you see skeletons of them, you can Google this. You can Google penguin skeleton. You'll see that they have pretty long legs that are covered in these layers of fat. Or you can keep warm by wearing a sweater.
This is a literal picture. Like this is a thing. This is not a Photoshop.
There's like all of these calls, like you hear about them getting covered in oil, and so there are like fundraisers to like knit penguins sweaters. I think it's really just to make the money, the fundraising part. I don't believe they actually put the sweaters on the penguins, but there you go. Okay.
So I want to throw this in because this is so I mentioned earlier that example of regional heterothermy, the countercurrent flow. I used to think about it a lot because I wanted it. So in my life before being a professor, I taught whitewater kayaking, canoeing, and took people rafting all over the world, and did it a lot of times at very cold temperatures. This is a little picture in a little Swift, but it's -20 out. And so as you're paddling, the air temperature is -20. The water's pretty cold. It's still fresh water, but it's pretty cold. And as you're paddling there, you know, or I knew as I arrived, that my hands were going to get really, really cold, and my head was going to get really, really cold if I was rolling or something. But as you're paddling along, there's an amazing thing that you just, it's a hopeful, it's the paddlers and it's the fish filleters on ships in the ocean and in the Great Lakes here as well. Their onset time. So that figure from 0 when your hands are immersed in the cold water to say 5 to 10 minutes when you're going to have this counterintuitive cold induced, not vasoconstriction, which is like the constriction of that venous system to say keep the core proper and at the necessary kind of homeostatic constant that it needs to be for us, and forget the distal areas. There, if something's going to get lost, they're lost. But in this 10 minutes, there is a pulse, and the venous system opens up, and it feels delicious. And your hands can rise, that it can rise, maybe not to what it would be normally, but it can increase up to 10 degrees Celsius. And so you're out there, and it's -20, and you're in the water, and the world is quiet and beautiful, and then all of a sudden, you'll feel this like, this like gorgeous release of warm you back into your distal system. And then it contracts again, because the main goal is to keep this, your core. But this is an example of how we as an endothermic species, there are other small adaptations that we have. We don't actually understand all of the underpinning of this. We do know that it varies by age. It varies by how frequently you do it. So there's an acclimation component to this. So if I was to join, I haven't done this in a couple of years. So if I was to go out and do this, I would get cold, and probably the blood wouldn't come back the heat wouldn't be released as quickly. And alcohol and there's a whole bunch of things that change this. But this is a small human example of cold adaptation that is trumped by complete immersion. And I think you've heard some stories of complete immersion, because complete immersion means core critical, shut off everything else.
Great. So we've been talking about adaptations to the cold, and we've been talking about them at different levels, right? And with penguins, penguins is an example where we do have adaptations to the cold at the level of the population. So we talked a little bit about the polar bears. And so here's a kind of way of going through the biological scales of organization for penguins where we do have an adaptation to cold at the population level because they do huddle together in populations, right? And then, of course, at the organism level, penguins are super fat, and they have very, very dense feathers, and they have reduced flipper sizes, like reduced wings. They have reduced beak, and sort of any kind of thing that would expose, that is, exposed to the cold is very small relative to what you might expect otherwise. And of course, then at the organ system level, the countercurrent heat exchange, and then of course there are a whole bunch of other adaptations. But penguins are really good, not just because I have a bias for them, but because they also kind of have a whole bunch at different levels that we can learn about.
So you can imagine in a final
Yes.
quizzy exam, maybe these are systems in which we might think about.
So we've kind of done the homework for the penguins a little bit. So what we want you to do is here we figured it out. We figured it out more or less. We've argued about some of these. There are certainly things that could be in other areas, that type of deal. So take your time, look at it, and see whether or not you agree with them. And also then, as you kind of learn a little bit about how this table can be filled out, you can then go back and try to do a similar thing with the polar bears to see whether or not it becomes a little bit easier to understand sort of where everything might be able to go on the table.
Do it for yourself.
Yeah.
The peoples.
The peoples. Do it for humans. Ooh. Yeah. Nice. Okay.
This is a chin stroke penguin.
Yeah. So.
Non sequiturs.
Non sequiturs. This is like the kind of the end. This is like the this is the last part.
Cue the Green Day.
Yeah. If you remember, at the beginning of the physiology unit, we asked you a bunch of questions about what you think about climate change, what you hope for climate change, and how you're interested in it. Like, there are different ways of being interested in climate change, right? And one of the things that we've been learning over the years is that there is a real change in focus, right? From people wanting or being interested in studying climate change, to basically document what's happening, if it's happening. We're kind of moving away from that, sort of, is climate change happening, to what are the effects of climate change, to now we're starting to see, how might we be able to mitigate the effects? And so that's kind of taken a really transdisciplinary approach as we realize that this is a wicked problem. Wicked is a technical term in business to describe something that is complex, that requires...
Also on the East Coast.
Yeah, it's wicked hard.
That's a wicked problem.
But these wicked problems require sort of these multidisciplinary approaches to be able to solve them. So if you remember, we asked you, we already asked you this question, but if you'd like to go ahead and annotate, where in the world are there going to be the greatest average temperature changes, or where are we seeing them now?
That was me.
Okay, super. So I believe that's what most of you said the last time, and you're totally right. So that's really great. The poles for all of those sort of physical properties that we talked about at the beginning of the unit,
greatest absolute value for sure.
Yeah, for sure. Okay, so we're gonna clear, because now we're gonna ask you another question. Where would you anticipate the greatest decrease in alpha diversity after the effects of climate change? Delightful.
Grab that. I love it.
Very, very, very good. Well done.
Show the pointy bits of the map.
Yeah. Super. Super.
Yeah.
Oh, I feel like
We're done.
we're done.
All right.
You're amazing.
Good luck.
Okay. No, sit.
Okay.
Okay, you screenshot that?
Oh, yeah.
Okay. Okay, let's clear. Where, oh wait, next map. Where might you expect the greatest increase in alpha diversity after the effects of climate change?
Trickier.
Cool.
Uruguay.
Cool. Very good. Okay.
Got it.
Super, super good. Yeah. So the Arctic, for example, what we're seeing is an increase in alpha diversity, right? So the number of species that are able to survive in Antarctica is increasing, and those who are living next door are starting to expand their range, right? It means that the Arctic is becoming greener, right? It means that bears and other sort of more temperate mammals are moving farther north. It also means that invertebrates are moving north.
Yeah, many. We had a slide that talked to like one slide that has a great number of like examples on it. One of them was like the doubling of fox diversity that's happening in many parts of the north because the Arctic fox, which is not going to go extinct anytime soon,
No.
but is being joined in many of these areas by vulpus, the red fox that if you're around where we live right now, because it's moving north. So a doubling of diversity in that taxonomic category, and that's happening in a bunch of different areas, a bunch of different parts of the biodiversity space.
That's right. And so, one of the things that is really important to note is that an increase in biodiversity, an increase in alpha diversity, is not necessarily a good thing.
Yeah.
Right? I mean, there are a lot of people. We have 35,000, I think, is the latest population census for people that live in the Arctic. The vast majority of them are Inuit or other indigenous groups, and I'm sure if you ask them whether it's a really good thing, the answer is probably no. And we need to kind of take our understanding of biodiversity and the way that we value biodiversity and always add this critical lens, right? Somebody says, does alpha diversity decrease around the equator because it becomes too hot? Yes, right? Things are going extinct off the top of mountains because it becomes too hot, right?
So all those things that were specialized in a tropical perspective to living in a very limited or special at that place environment of being cold and wet, as that temperature marches uphill, as it marches up latitude in Canada, as it marches uphill there, those species in the cold, wet forests, there's nowhere colder and wetter to go. So they are the literal polar bear equivalents. Mm-hmm. That at some point when the polar ice is gone and the bears can no longer eat the seals, that one species will be gone from the Arctic. But there's literally thousands of cloud forest specialists of plants and animals that will go extinct.
This is an important question. So the equator species don't shift its range north or south; they just go extinct. Both.
Yeah.
So what's happening is in the equatorial regions, either the species goes extinct or it shifts in range. Either way, you're going to have a drop in alpha diversity, yeah. Right? So a drop in alpha diversity can be because of a range shift or because of an extirpation or an extinction event.
And there's an amazing observation, natural history observation, that because temperatures in the equatorial region, in the tropics around the world, are generally more stable, the species that live there lose the capacity to deal with extremes and variation. And that in turn leads to things that can't disperse through changes very well at all. So the capacity to move, so the caribou and the other things in the north that we see covering thousands and thousands of kilometers, there isn't a tropical equivalent of that because in the tropics you get good at that temperature, and that temperature is kind of always there, and it's been there for generations and generations, and so you don't move very well, and so you can't follow. If your temperature is leaving, you can't just kind of pull up the stakes and follow it, because you've lost, maybe in some cases you've lost the capacity to fly, or you've lost the capacity to deal with either hotter or colder events.
Yep.
So you're kind of screwed in a bunch of different directions.
Yep.
Yep.
And even though you may be able to move further north, that's not necessarily a good thing for the things that are already further north, right? For the people, for the other species that are there, you know, one of the important tenets of global biodiversity patterns is that in the poles, though there is low biodiversity, it means that there's low competition. And if you increase that competitive environment for the things that are already there, then you've got a problem. And that's why alpha diversity is not really the best indicator of ecosystem or biome health, right? Because
it's very sensitive, and you have to know what you're measuring.
That's right.
So one of the things that's happened as an observation about in the north, we have a book, maybe in the other room, to the insects of Nunavut in Arctic Canada. And that book is amazing to me because it has descriptions of those in French and English and Inuktitut, and names in all three languages as well. And one of the things about this book, even now, and this is maybe 3 or 4 years, a book that's 2 to 4 years old, is that there's many of them where in the Inuktitut section they're like, well, our elders, we don't have a name for this because our elders, this is new, that we've seen this. It's literally, this is not an organism that has lived with us for thousands and thousands and thousands of years. Yep. This is new. So what do you want to call it?
Well, and that's it. And so as, you know, scholars in Inuktitut language, in the Inuktitut language, are adding words like technological words, right? Computer, mouse, all of that stuff that, you know, we've done in our different languages as those things developed. They are also adding new biological terms, biological words
bumblebee.
To there.
What should we call a bumblebee? Because this is new.
Yeah, exactly. Okay. So, if you remember,
we could go on and on.
We could go on and on, but we're not, because...
Oh, can I have one more some of these questions from that? Would extinction be more likely to be driven by temperature change or invasive species, or both?
Yes.
You'll have different opinions, but I think the
proximate ultimate
omnipresence of the temperature changes is just, it's going to facilitate, it'd be very hard or impossible to extract them. But the temperature, the changes in precipitation and temperature are just, and dependency of those things is it just trumps or envelops all of the other things.
Yeah.
In the cases where we have moved species that become established, that's going to have in that place a really important effect, maybe deleterious effect, maybe another one that increases the diversity initially. Yep. Because it adds species. Yep. But Yes, and I would say more the abiotic thing, the changing, the climate crisis. The
climate crisis, the abiotic thing is sort of the ultimate driver, right? That can lead to invasive species, right? So that's a proximate cause. And then you kind of you add on not only the invasive species, but the sort of the testing of the limits of the physiological systems of those individuals. And then there's no chance, right? Okay. So we asked you a while ago, way back in the beginning of November, so not that long ago, what you thought was probably going to happen. And if you remember, most of you said D, and it was kind of like a checklist, right? So what we want you to do is let's review this checklist. There's dramatic changes to many populations, migration of some species farther north, invasion of some southern species, overall decrease in biodiversity, some landforms will be altered. And this was specific to the Canadian Arctic. Which one of these things, after our just discussion right now, would you cross off this list? Which one is not true? Yeah, that's cool. Good. Good. Yes, and of course, then some of these other statements at the top, like little direct change, that's also not true. So take that off the list. Good. Okay. And then within D, one of the things that is most likely very not going to happen is a decrease in biodiversity in the Arctic. It's actually going to increase. So we've talked about alpha not being necessarily the appropriate metric, especially if you're doing like science communication. People always think that more is better. And so if you tell them that there are more species in the Arctic than there have ever been, they'll be like, well, that's a good thing. And like, no. And so and then having to like change that misconception can actually muddy the communication. It's not really an effective SciComm approach. So what you want to do is you want to find like the simplest message, the one that is most clear, that doesn't require the it depends, right? The it depends stuff is for us. It's for like biologists, right? Like you guys totally now get that it depends. But if we're going to communicate this outside of our own world, then we're going to have to maybe focus on a different metric. So here's what you said. Okay, so here is basically what you all said is going to happen. It is happening. We do see these sort of major increases in temperature at the polar areas. Antarctica tends to get overlooked in maps, but the peninsula area right here would also be, purple, would also be quite warm. And so what metric that we have in our toolbox for biodiversity measures do you think would be a better sort of starting point when we start to try to communicate to other people about the effects of climate change? Which are some of the other, we talked a little bit about those different indices. Which one do you think would be more appropriate to talk about? Go to the chat if you want, write it on the slide, whatever. It's a hard question, so.
Even as
Ooh,
Shannon.
that's a good answer.
This is the answer, but that's what we're.
That's really good. That's really good. Okay. Shannon question. So why Shannon? What could Shannon be used? How could the Shannon Diversity Index be used in order to help communicate the change? Okay, why does the South Pole experience less temperature increase than the North? So this is the South Pole generally overall is experiencing less of a temperature change over the continental part because it's covered in an average of 2.6 kilometers worth of ice. It's going to take a long time for all of that ice to melt before revealing the dark background that will propagate and increase warming.
Remember the albedo effect?
Right, where it is happening to the same degree as the Arctic is right here on the peninsula. So this part should be purple because there is an average less ice there. So that has already melted and is creating this rapid warming. In the Arctic, the average thickness of ice is only a few meters, and therefore that has already melted and is rapidly warming as a result of the release of these darker backgrounds that absorb more heat.
And you can actually see where that's in the cases where it's not purple. So take a look at Greenland in the Arctic.
Right, here's a big ice.
That's an area that's a really important area. So as you listen, because it's so thick there. So if you hear in the news about changes in that ice sheet, those are catastrophic across a huge area.
Yep. And Greenland, the ice sheet is melting so rapidly. It's just going to take a few hundred years, and so we'll start to see the effects along the edges of Greenland as it melts, and it'll be catastrophic when it does. And so Shannon Diversity Index is an excellent way of talking about changes within that region or that habitat or that ecosystem over time. You would see changes in evenness, right? Where some species are becoming more competitive, more abundant at the expense of others. So you can see these fluctuations over time. That's a brilliant answer. The other index that would also be really important to talk about is beta diversity, right? beta diversity captures those changes, especially if you look at them over time. So this is what this particular pixelated map has done, is looked at sort of before and after projections of beta diversity, that is the turnover of species. So by removing the common ones and taking a look at how it's going to change over time, you can see that the predictions for the Arctic, as well as the mountain elevations in the Andes, are quite dramatic, right? As species either move up the mountain or move further north, because their more southern boundaries are becoming warmer and warmer.
So I think one thing that I would throw in here is that one of the reasons I love, and I study beta diversity patterns a lot, and I proselytize, I preach about it. And one of the reasons that I like it is because, and you said it depends is just for us, and I'm going to disagree slightly, because this is it depends. This is not just the absolute, but in comparison. This is it depends to another time or another space. And people get that. They might not, so don't lead with it depends, but you set it up in a comparative method. It's like, so these things were here, now they're there. Yeah. And these things were here, and now they're here. And then you find, from a SciComm perspective, you find the things that people care about. In the tropics, it's often ants, because people have an intimate relationship everywhere in the world with ants. And so ants that you would not see here, you now see here. That's a thing. And it's not the only thing, but it's a thing that people go, oh.
Yeah.
Oh.
Yeah.
And so beta diversity is literally the index of diversity to me of it depends. It's not about the absolute number. The absolute number is part of it, and you need to know the numbers before you can calculate this, as you remember, of course, as you all do. But to apply it subtly and intelligently, you need to, comparing in space or time.
Yeah. So beta diversity people get. Alpha diversity, it requires, I think, too much communication.
Yeah, that's kind of like, people will love sausage. They don't necessarily need to know what goes in it. So the alpha, those numbers, that's in the sausage. Present them with this beautiful barbecued vegan or vegetarian or lamb sausage, whatever is delectable on your table.
Yeah. And the connection between Shannon diversity and beta diversity is, for example, you might predict that Shannon diversity would be better able to detect sort of more subtle changes,
yes. Yep.
changes that are happening early.
Yep.
Whereas beta diversity, if you see changes in beta diversity, then things are like going to shit already, right? Yep. Things are changing like right now, it's already too late. Shannon can be used as a bit of a canary in the coal mine, yep. kind of indicator that things are going to be more dramatic or that things are going to change with respect to beta.
It can also tell you about the lay of the land, as it were. As you look across beta diversity, as it changes dramatically, if you're going across Ontario and you're like, oh, all of a sudden this area has changed a lot from that. It's like something different is here. This is another region or another biome, or like we use that in the tropics all of the time, because as you march uphill, you leave and enter new zones very, very quickly. And so it's the change, the relative change.
Yep.
Yeah.
So
now begins the second course, or the fourth unit on beta diversity.
No.
It will be given. This is just a thought. Some of you know this, some of you bumped into it, but all of the lectures are strung together in a playlist here, if that's of interest to you, to revisit them. And also, generally, all of the music that we used in the pre-class kind of bits, plus some that we didn't ever get to, is in this. So if you want some pump-up studying music that's not on your fruit-based device already, shuffle through that.
Who uses a BlackBerry? I feel like we can move away from saying fruit-based device. No, I know. But like you're being inclusive by saying like multiple fruits, but it's really just one fruit. They won.
This fruit did.
Yeah.
Yeah.
No one has a BlackBerry anymore.
But this is everybody won, so it's fruit.
Yeah, I know, but you can say apple-based device.
No, not in this, because we're not condoning. You can own whatever you want. We're not promoting. We get nothing from the big palm in the sky.
Mm-hmm. And the chatter will be endless in this room for, well, hopefully forever. Yeah. But we are...
Oh, ring,
yay!
Ring, 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 banana phone.
You have a BlackBerry! Yeah. Anais has a BlackBerry. Wonderful.
Yeah, stop dissing people's phone. I only have a banana phone. I've only had a phone for like 5 years. Before that, it was just the banana phone.
Yeah, let's say goodbye. We are ridiculously grateful to you, and it is not your job to keep us mentally healthy, but you have, and we are grateful to you for that. We are grateful to the opportunity to be able to continue to connect with you. We hope that you have felt somewhat connected, somewhat supported, because we have, and we have enjoyed every moment of it. The privilege of being able to teach together,
Yep.
and to be able to do it in this way has been wonderful and delightful. And we also recognize the extreme privilege that we have in being able to talk for how many hours? 24 straight hours?
I mean, most other places we'd have been asked to leave like so long ago.
There are not that many people that have a microphone that can talk to this many people for so long. And so we are extremely aware of that privilege and grateful that you've done it with us.
And another thing, as well as those thanks, is just to you are an impressive bunch. This is not an easy year, and this is never an easy course, but this is not an easy year. So, well done you.
Yeah.
Find someone in your physical bubble to give you a hug.
Yep.
And congratulate you.
Big pat on the back.
So,
You've done great.
well done you.
You will do great. And we will post all of the times that you can drop in and ask us questions as you prepare for the final exam. Thank you, everyone, for everything. And take care. And take care of each other.
Yep. Expect and deliver kindness. And now,
And now.
this.
Bye.
See you in a second.
If you're
hang
going
around.
to stick around.